Hi friends, today we are going to see a method of decreasing sampling rate of a given signal, which is also known as a decimation or a decimator. So we have so far seen what do you mean by a downsampler, and we are going to proceed today to decimator. So there's a very basic difference between a downsampler and a decimator. Okay. First, we will analyze the signal in time domain and frequency domain, how it looks if we have a downsampler, and then what does it puts the effect if I'm shifting from downsampling to decimation. Okay. Before going into any further, I just wanted to set apart the differences. Downsampler is a process of just reducing the sampling rate. So if I'm downsampling by a factor of d, then if I have x of n signal, then I will generate some x of y of m signal. Here the sampling rate is fx, here the sampling rate is fy. Okay, so I'll just downsample the signal without taking into any consideration whether there will be, after downsampling, whether there will be aliasing or no aliasing. I really does not care for it. Okay, that case we say it to be downsampler. But when I am saying decimator, that time I will take care that there is no aliasing and the signal will be reconstructed more faithfully as compared to downsamplers. Okay, so when I say decimator, the block diagram becomes a low pass filter with a transfer function h of n or an impulse response h of n, followed by a downsampler of factor d. Okay, so here I have x of n which works on the rate of f of x, and here I have f of y which is giving me y of m. Okay, so this is what the basic difference between a decimator and a downsampler is. A downsampler is just downsampling the sequence without taking consideration whether there will be aliasing or no aliasing. But in decimator, we will take care that there will not be or minimal amount of aliasing would be taken. Okay, so I will say that in decimator I will be using downsamplers, okay, and also filters, so that I can avoid aliasing. Okay, so this is what the basic difference between a decimator and a downsampler is. So let us first analyze a downsampler, how it looks like into or what will be the output, that is y of m, in time domain and in frequency domain. So let us analyze the signal in time domain and in frequency domain for a downsampler. So this is my downsampler. Now in a downsampler, I have let's say I draw the diagram again. I have the system which decreases the samples by a factor of d, and this is my x of n and this is my y of m. Okay, this is working at fx and this is working at fy, which is equal to fx upon d. Okay, now what we are going to do over here is, we know that if, let's say, for example, if I take an example of d to be equal to 2, okay, then if I draw the signal x of n with n as my x axis, and let's say I have a samples given as some random sequences. Okay, let's say these are my random sequences. I am not concerned about the amplitudes because I am not working with amplitudes, but I am concerned with the times. Okay, let's say this is my 0, this is 1, this is 2, this is 3, 4, 5, 6 and 7. Okay, so there are total 7 instances given over here, 7 values of n. and I wanted to downsample this to a rate of with a rate of 2. So what I am going to do, I will be picking up the first sample, that is at n is equal to 0. Okay, that sample will be picked. Then I will skip first sample, because how many samples should be dropped? To reduce the sampling rate, d minus 1 sample should be dropped. So I will be dropping d minus 1 samples. Okay, so I will drop this sample because d minus 1 is 2 minus 1 is 1, so I will be dropping 1 sample. So I will not consider this sample. Then again I will consider the second sample, and then I will drop this sample and I will consider this sample. I will drop this sample and I will consider this sample. So my y of m will be, this is my m, this is my y of m, will have the first sample which is n is equal to 0. Then the second sample will be of 2. Correct? So this is, as far as m is concerned, it is 1, but if n is concerned, that it is 2. Okay, this is, I put like this, m is equal to values and n is equal to values. Your n is 0, your n is 2. Okay, then I drop the next sample and I pick up the next sample. Your m is equal to 2, but n is equal to 4. Okay, then I drop the next sample and I pick up the next sample. Here n is equal to m is equal to 3, but n is equal to 6. Okay, so how we can write, or what we can say from this relation is y of m is equal to x of n into d. So I will be picking up the dth sample. Okay, n will be taking all integer values with respect to, therefore this will be integer multiples of d. So I will be only picking up the integer multiples of d in y of m. So we can develop a relation as y of m is equal to x of nd, where n takes the value as, where n is equal to 0 because it is coming 0. Okay, then I can have a signal which is going in the negative axis also. So I can have plus minus d, which is 1d, then plus minus 2d, and so on and so forth. Correct? And it will be 0 otherwise. So any other integer, any other value of n will return y of m to be equal to 0. Correct? So this will be my relation, very important relation we need to take care of, because that will be needed in the derivation of decimation. So we have y of m which is equal to x of nd, and n will be equal to integer values of integer multiple of d, that is 0, plus minus d, plus minus 2d, and so on and so forth. Okay, so I hope that you have understood the relation. But then how to achieve this, or how to downsample this, how to remove the samples? So we will use a very basic and a crude methodology to do this kind of a operation. Okay, what I am going to do is, wherever I wanted to neglect the samples, I will multiply it with 0. Simple. Because multiplying, let's say, this signal with 0 will return back me 0. Now if suppose I multiply with a sample, if I keep 1 over here, then a 0, then 1, then 0, then 1, then 0. Okay, then what it is going to happen, what it will be giving me, it will be giving me a new sequence which is nothing but comprises of ones and zeros. Okay, so let us understand how to do this. So what I do is, I take my x of n, okay, and let's say this time we will use a cosinusoidal waveform. So I am considering a cosinusoidal waveform, and these are my amplitudes. Okay, now this is going till infinity. So this will be going to infinity. Now what I'll do is, I will take the example of, let's say again decimation by a factor of 2. So I have to drop d minus 1 samples, which is nothing but 1. So I will drop d minus 1, which is 1 sample. Okay. Now this is my n again, and I bring a new sequence p of n, just a p of n sequence. What it will give me is, I will be multiplying this. Now when I wanted to drop this sequence, right? So there should be 0 just below this. So there will be 0 at this point. I don't want to drop this sequence, so there will be a 1 at this point. Okay, I don't want to drop this signal, so there will be again 1 at this point. I don't want this signal again, and so on and so forth. So I will have 0, alternatively 1, then 0, alternatively 1, then 0, 1, and so on and so forth. It will go on. Okay. When I multiply them both, that means, let's say that I get a new sequence. So what is new sequence? New sequence, let's say C of n I say. What is C of n? C of n is nothing but P of n into X of n. Okay, when I multiply these two sequence, what is going to happen? Okay, I am going to get, wherever there is 1 in the P of n, there I will find the value of X of n. Rest everywhere it will be 0. And P of n, the samples are placed at integer multiples of d. I have kept it to be 1. So I will have the first sample at 0, n is equal to 0. Next sample, that is next one, will be at 1d. Next 2d, and so on and so forth. Okay. So this will be the section, or this will be the periodic sequence. So I say that P of n is a periodic sequence of pulses. So I can, if P in is a periodic sequence, okay, let's say, let's not go into that first. Let us assume that I am getting a new sequence now, C of n, which is P of n cross X of n. So what will be C of n look like? N, and I am drawing a new function C of n, correct? So what is C of n? C of n is nothing but, here I will get something, so it will be high over here, then a 0, then a much lower value, then a 0, then a negative value, then a 0, then a highest negative value, then a 0, then a lowest value, then a 0, then some value highest like this, then a 0, then its next highest, and then a 0 likewise. So wherever there is zeros, I am going to get 0 values, and wherever there is 1, so it will be C of n. Okay. Now I will compress or remove the zeros and pick only the non-zero terms. So I want only the non-zero terms. So now my y of n is nothing but C of md or nd. Okay, we can keep y of n or y of m, that's not an issue. So now n, and this is my y of n, which is nothing but C of nd. Okay, and then I will pick the first sample, then I will place the next sample, then the next, then the next, then the next one. So what I did, I dropped all the zeros and combined and progressed and got only the sequences which are non-zero. Okay, so you understood. So here what we have is X of n, then I got something called as P of n. I multiplied P of n with X of n, I received C of n, and I picked up only non-zero values, that is giving me Y of n. Okay, so now I got my Y of n. So this is a basic process that I will be doing. Now let us understand mathematically what does it looks like and what it is. Okay, now we have P of n, which is a periodic pulses periodic impulses. Okay, so if we take Fourier transform, okay, or we can write P of n as like this, because it is periodic in nature. I can take I dt f t formula and I can use it, and I can write it like this: d is equal to 0 to d minus 1, because the period is d. I goes from 0 to d minus 1 because the amplitude is 1, and the twiddle factor e raised to minus j k n by d. Okay, P of n is periodic pulses with period of d. So I have periodic pulses of period d, so I can take its IDFT and I can write as P of n is equal to 1 by d. I goes from 0 to d minus 1 because the amplitude is 1, e raised to j 2 pi k n by d. Okay, now we know that C of n is equal to x of n into P of n, correct, and x of n, okay, x of n into P of n, and y of n is equal to C of, let's say, some variable you can call it, or you can keep it as it is, n d. Okay, let us keep y of m. I'll keep y of m. Y of m is equal to C of n d. We know that, okay, from the previous diagram. So I can say that C of n d will be equal to x of n d into P of n d, just change of variable, correct. Now if we take the Z transform, okay, if we take the Z transform of y of m, so we take Z transform of y of m, we get y of z. Y of z is equal to summation n going from, let's say, minus infinity to plus infinity, okay, or m going from minus infinity to plus infinity, y of m z raised to minus m. So now I will substitute the value of y of m in place of this, which is equal to summation m goes from minus infinity to plus infinity, C of n d, okay, or C of m d n d into z raised to minus m. Okay, now it is really getting haphazard, because we will get two variables. So let us stick to one variable. So I'll write md, okay, C of md. Now C of md can be written as m is equal to minus infinity to plus infinity, x of md into P of md z raised to minus m. Okay, now what I'll do is I'll write like this. Okay, now I'll write like this. P of md, according to the definition which we started, x of md and P of md can be written as summation, okay, d or k going from 0 to d minus 1 with a 1 by d over here, okay, 1 e raised to j 2 pi, okay, nk by d, and the whole thing is multiplied by z raised to minus m. Okay, fine. Now what I'll do is I'll interchange or change the variable, or we can say that in the given equation we can see that the samples will be only picked up, or we are only interested into non-zero samples. So when I am only interested into non-zero samples, I can easily convert this to m, and I can make this go m by d. So this shows the the spreading of the signal or the effect of the shifted replicas of the spectrum. And then you see that the magnitude is been reduced by d. Okay, so these all things we can observe. We have shifted version or shifted replicas of x of d, okay, x that is the input signal, by a factor of 2 pi k by d. D is the decimation factor, because here you can also have omega x. How I can bring omega x? We have already derived that omega y is equal to omega x times of d, okay, d times of omega x. You can put it and you can get everything in terms of omega x. So it will be 1 over d x of e raised to j omega y can be written as omega x into d divided by d, which is nothing but omega x, e raised to j omega x, which is nothing but the spectra of the original signal. So what is happening? We are having multiple spectrums, okay, of x of j omega, which are being shifted by k value, and how many such shifting will occur? That depends on the factor of k. So that much of aliasing will occur if I do such kind of operation. Okay, then moreover we have reduced the amplitude by a factor of d. Okay, so what does it gives me? The knowledge that looking at the equation I can say that the amplitude is scaled by 1 over d. Second, the original input spectrum is shifted by k samples, and k depends on d. What is d? D is the decimation factor. Okay, so these all things we can observe from the equation of a downsampler. So this actually gives you the insight of what is actually happening mathematically in a downsampler. Now once you know the downsampler, it is really basically very easy to prove what will be the output for a decimator or a decimation process. So in decimator, I have an input x of n given to it will be given to a low pass filter with an impulse response h of n, which is again given to a downsampler by a factor of d, and I will be getting y of m. Correct? Now here the rate is f of x, here the rate is f of y. Okay. Now let's say I called an intermediate dummy variable v of, let's say, n over here. Okay. So now what is going to happen is the output of, I say that the output of filter. So for the output of filter, v of n will be equal to, using convolution, I write n is equal to minus infinity to plus infinity. Okay. H of n minus, this will be k, n minus k into x of, let's say, k. Okay, this will be my input or v of n, and this v of n is going to be given to y of m. So now my y of m will be equal to v of md. Okay, so instead of now getting x of n as an input, I am going to get v of n as an input, which is v of md for m taking 0 plus minus d plus minus 2d and so on and so forth. Okay, so only change in my derivation will be, I will have y of z now, which is equal to same way 1 over d summation k going from 0 to d minus 1 instead of x I will write v. V is equal to e raised to j 2 pi, okay, e raised to minus j 2 pi k by d into z raised to 1 over d, okay, and v of z will be equal to h of z into x of z, which is nothing but convolution property. Convolution property says that time domain convolution becomes multiplication in the frequency domain. So if I substitute that, my y of z will be equal to 1 over d summation k goes from 0 to d minus 1. Now I will get h of what? H of e raised to minus j 2 pi k by d z raised to 1 over d into x of e raised to minus j 2 pi k over d into z raised to 1 over d, correct? Then if you substitute z is equal to e raised to j omega y, then you are going to get e raised to j omega y 1 over d summation k goes from 0 to d minus 1, okay, h of, okay, if I substitute over here, I am going to get omega y minus omega y minus 2 pi k over d and x of omega y minus 2 pi k over d. Now this is just another way of representation. Everywhere z is e raised to j omega, you can write here y of e raised to j omega y and h of e raised to omega y minus 2 pi k by d and x of e raised to omega y minus 2 pi k by d. This is well understood. It is one and the same. Okay, so this is what the process of decimation proof. So whenever they ask you the process of decimation as a proof, you have to prove by showing the decimation as a process by saying that you will have a filter in the starting and then a downsampler, because we need to restrict our spectrum of the input signal to avoid aliasing, and then we will have a downsampling process. So the output sample will be now convolution of the impulse response of the filter and the input samples. This whole thing will be given to the downsampler, and then I am going to pick up only the integer values of m. That will actually give me the downsampled version, that is y of m. And the derivation, we have to start with m, then we will go to in between we have switched to n, and then we have applied Ztransform to obtain the frequency characteristics of the signal. So this is all about a decimation process. I hope you have understood what how to proceed or how to derive a decimation process.